We'll start with what is IO-Link, just a baseline to get everybody on the same page here. IO-Link is point-to-point communication. We've got a couple of bullet points. You can see the cable lengths, the cycle times, but essentially what we're looking at here is three-wire communication. We've got power, we've got our ground, and then we've got a communication wire, a serial-based communication. So it's just a low-cost way to get communication in a very simple format. IO-Link is not proprietary to one sensor or actuator manufacturer. IO-Link is made up from a consortium of 232 members, always adding members. This is as of May 2019. Go fast. This is as of May 2019. There were 232 members. We're always adding members to this consortium, but together all these companies came together to create a low-cost, easy-to-use, efficient way that sensors and other low-cost objects can communicate more data than just a switching output. You'll see on there a link in the middle. It's io-link.com. That is the link to the consortium and also more resources to learn more about IO-Link. So now in my own words, if people ask me, I get the question often, what is IO-Link? Why do I need IO-Link? Why can't I just use Ethernet IP or Profinet, something else? So we'll use this example. This is a LiDAR scanner that can measure many, many different things. Not only does it measure position of objects and kind of the spots where they are, angle and distance to that object, but it's also at the same time measuring more parameters that might have an impact on your application. We can measure the light levels, the signal strength. We can get a dirty lens warning. We can get a temperature reading. We can get operating hours, timestamps on trigger points. There's a lot of extra information that we can get out of these scanners, these high-end scanners, and because they are kind of a higher cost item, it's the ability to talk to Ethernet IP, Profinet, or EtherCAT isn't a huge dollar adder to be able to add all this information up to the field bus level. Okay, so in many cases, the capability is already there. All they got to do is turn it on. So in these higher end applications, we're getting extra information. But when we start to think about lower end, think of small inductive procs, one of the simplest, lowest cost sensors you can get. When you start thinking about those lower end sensors, internally we actually can measure many of those same parameters, but because we aren't spending a lot of money on the communication, it just becomes cost prohibitive to be able to add that communication up to a field bus level. So we've gotten kind of stuck to just giving a switching output. That's all we're going to get out of a low-end prox, if you think of anything that you have in your machine today. And again, the truth is these sensors do have the ability to measure this information. We just don't have the ability to communicate it up to the field bus level. So with IO-Link as a bridge, it's a low-cost way to spread out kind of that communication level. Instead of running Ethernet in our low-end proc sensor, we run 8 proc sensors into a block that talks Ethernet IP. And the way that they talk to that block is IO-Link to get all of this extra information. Low voltage, cycle counters, timestamps, all kinds of different things. We can change our threshold, adjust the switching distance on an inductive sensor so that you get a warning before something hits that sensor. Many different things we can do. So that's just a quick overview on what is IO-Link. Now we'll talk about some of the benefits and why I should use or why I think you should be using IO-Link. So this cutout on the left side of the screen, that's a cutout directly from the consortium website. But essentially what we're looking at here is how IO-Link is really the future of Industry 4.0, industrial internet of things. We need to be able to understand what's going on in our process all the way down to the sensor level. The more information we can get, the better that we can go back and look at that information, analyze it, and find a root cause for some sort of an issue that our product experienced. I like to use the analogy of an iceberg. Traditional I/O, your switching outputs that you're getting today out of inductive sensors is just the tip of the iceberg. Underneath is 90% of what that sensor is doing, and IO-Link enables us to see that information. you can look at your process and you say, okay, a timestamp is really important to me. I want to pull that out and get a timestamp every time there's a switching occurrence or a switching event. Or maybe the internal temperature is important. I want to pull that out. You can see what's going on under the hood, and you can utilize that in your process. So getting back to the three major benefits, I'll go through these in following slides here, but we've got simplified installation, we've got automated parameter setting, and we've got expanded diagnostics. So the first one, simplified installation. This comes in a number of different ways. First off, it's just physical wiring. So we've got here a panel on the left and the right. On the left is hardwired. We've got 80 different sensor signals coming into a PLC. And if we're looking at standard I/O, every single one of those sensors has to have its own signal, its own wire getting terminated in the PLC. So we've got 80 wires coming back. Typically, we're using passive connectivity blocks. So you've got a cable that's got 18 small pins coming out of it that we've got to strip them all and terminate all of those connections. With IO-Link, we actually can get up to RJ45 Ethernet connections, so you don't have to terminate any wires in your PLC, but there are also versions that can terminate the IO-Link connection in the PLC or in the cabinet rather than out in the field. And here's an example where we terminated our connections in the cabinet, and there were only 12 wires for those same 80 sensors. And for these connections, we're using M12 4-pins across the board. We don't have any special multi-core cables that typically are higher cost and longer lead times. Overall, in this example, for 80 sensors, we had 75% less physical wiring. Once again, just as a visualization here on the left, this is our standard I/O. We've got a passive connectivity block that goes to an 18-core cable where we can terminate every single connection that we have, every single switching output that we need to monitor. And on the right, we have IO-Link, where we're showing an IO-Link master. We've got 8 ports at the bottom. Those are where we connect our sensors to. And then at the top, those 2 connections at the top, those are upstream and downstream Ethernet connections for Profibus, EtherCAT, Ethernet IP, whatever field bus you're talking, we are bringing those IO-Link signals up to the field bus, just converting those signals. And if we look at our overview, our system overview or map, we've got, again, at the top, we've got our PLC talking to an actual PC where we can run that information wherever it needs to be. But at the sensor level, we've got sensors coming into a passive connectivity block, and then we're terminating individual wires. Again, in this view, I've got my iceberg on the right. We've just got the tip of the iceberg. All I can tell from each of these sensors is yes or no. Something is there, something is not. That's all I get. If I get a failed product coming down my line, all I can see is whether or not these sensors are on when that product comes by. I have no history information. I've got no other variables that I can track and test to see what might have caused that issue in my product. In this version, utilizing IO-Link, we can have the same sensors. IO-Link's available in almost any standard sensor that you have today. We can have the same sensor performance, but we can get access to that extra data. And it is simple. It's not very hard to implement IO-Link. We are changing from passive connectivity blocks to active IO-Link masters, and then we're changing our multi-core cable connections to Ethernet connections, going from, you'll see at the bottom of that Ethernet connection, it's an M12 4-pin connection, and it goes right into RJ45 connection that we connect to your PLC. You can also do ring star topology and connect it right into whatever other Ethernet devices you already have in your machine. When we do this, we get access to that extra information. Think about timestamps. Think about temperature warnings. Think about trigger cycles. How many times has this sensor switched back and forth? What is the average trigger time? There's many different things that we could get out of these sensors that enable better root cause analysis and better troubleshooting. The only difference that we're going to see here as we go from our multi-core connection to our IO-Link connection is instead of terminating 80 pins in the PLC and physically connecting all these pins, now we automate our connections and we're going to have to add in one more EDS file and one more set of add-on instructions. So sometimes these blue boxes can be a little bit confusing to people. but what I can say is this is like setting up your PLC program. You set up your logic in your PLC, and as soon as you've got that set, you lock down your code, and then you just load it every new machine you go to. This is something that we can automate. We can automate those EDS files, the add-on instructions, the way that we pull that data, so that now we don't have to terminate 80 different wires. We just have to load our PLC program. So it's actually automating a piece of setup that previously there was no way to improve, getting somebody to terminate a wire faster. Okay, our next pillar of IO-Link is automated parameter setting. So this allows us to do really fast and easy and accurate. We don't have to worry about operator error changeovers. Okay, so in many of our machines, we're running different sized objects, smaller boxes, bigger boxes. We're running different colors. We've got our Christmas candy bar, we've got our Halloween candy bar, whatever it is. We want to run Pepsi, then Coke right after each other. Whatever you want to do, we've got different colors we're dealing with, and then we've also got different surface finishes and glossinesses. I come out of an application engineering role. I can tell you that all of these changes are really simple for me to take care of. All you got to do is just adjust the sensor. They typically got a potentiometer on it or a teach button. You go ahead and adjust the sensor, it'll be able to compensate. We've got great sensors that can detect both of those. The issue is you have to actually touch the sensor to make the change. So when you guys as a customer are running different products and you want to do a changeover, however many sensors on your machine, you've got to go touch all of those sensors to make those changes. IO-Link allows us to make those changes electronically. So we can either triggered from the PLC, maybe through your HMI, you can say, hey, run recipe B, and it will connect to all of your sensors on the machine and change their parameters over to recipe B, whatever you predefine as that recipe. You also can have sensors that say could measure a size of an object. They could recognize that you have a different object in there, and they could tell the rest of the machine, hey, we've got another object coming through. Let's change all our parameters while this object comes through so that we can reliably detect it, and then we can switch back to our normal parameters when we get back to a smaller object, whatever it is. This is where we start to enable that one-piece flow, or lot size 1, something like that. Okay, the third pillar of IO-Link is expanded diagnostics, all the way down to the device level. This is that root cause analysis. When we want to figure out what's going on, if I'm building a bottle of pop and I get to the end of the line and I'm missing a little bit of glue on the label, why am I missing that glue? Did I run out of glue? Did my glue head get clogged? What happened? Was I misaligned? I don't know what's going on there. Sensors can help enable what's going to be happening in your machine. They can, sensors can start to tell you what's happening in your machine. You could have a sensor right before that glue head looking at the length of trigger on the label. If the label doesn't get glued down, it sticks up, and then you've got a longer, using air quotes, a longer bottle as it comes down the machine, and you could detect that early before you fill the bottle with pop and then have to discard that wasted material. So expanded diagnostics is something that we can give examples of, but it is really something that our customers are going to find the innovation before I tell you about it. We're going to look at different parameters, again, trigger times, temperature warnings, lengths of triggers, cycle times, and timestamps, different things like that. They're going to start to enable more and more troubleshooting in your machine, earlier warnings so that you can identify an issue before it gets to the end of the line and you have to scrap material. Here on the screen, I'm showing an example of a photoelectric sensor. That black line that goes across the screen, you can see it kind of dance around. That's actually the light level that the sensor is reading as a bottle comes across in front of the sensor. So you can see the leading edge of the bottle, the black line drops really low because a lot of light is absorbed by the leading edge. And then in the middle of the bottle, it's pretty clear. You can burn through it. Our light levels kind of dance back up high a little bit. And then we get to the trailing edge of the bottle again. It's a very solid signal. We could start to read that and we could see if, hey, the middle of that bottle is giving me false triggers. Why am I getting 2 trips on every bottle I see? We dig into our IO-Link data and we can see that, hey, actually, that light, maybe aqua line, is low enough that we're triggering our threshold to go back on. Let's go ahead and adjust our threshold in the sensor so that it doesn't get this false trigger from the bottle. Many, many different ways that we could play with it, but this is just one example of where we can get expanded diagnostics. The other example I like to use is inductive sensors or magnetic cylinder sensors that can tell you the temperature of something within your machine. An inductive sensor is often deep in the machine, really close to maybe a motor or a gearbox. We could get you early warnings that, hey, something's heating up, you might want to take a look at it, maybe got to change the oil out. Whatever it is, we can get early warnings to try to prevent failures in the future. Magnetic cylinder sensors as well, if you're looking at pneumatic cylinders, we can give you early warnings on temperature and that kind of thing. Okay, the last couple of slides here, I just want to go over a couple of products using IO-Link. This isn't something that is niche to SiC or to a certain sensor type, photoelectric sensors or something like that. IO-Link is very widely used by both SiC and other manufacturers and many different sensing technologies. So this is actually a screenshot from, again, the consortium website, io-link.com. You can click on any manufacturer and it will tell you all of the IO-Link sensors that they can offer. So the blue lines at the top are actually the interfaces that we can offer, and then all of the green options, starting with encoder, are the different sensors and devices that we can offer that actually can give an output in IO-Link and provide that extra value. So here's one look at it from the consortium, and then here's my biased look at it, filling up a whole slide of all the different sensors that we can offer that today have IO-Link on board already. We go from the top, encoders, you've got a picture right next to it, but we can go TTL, HTL, or IO-Link as well. We've got pressure sensors, level, both ultrasonic and physical probe, microwave probe, temperature sensors, inductive proximity sensors, ultrasonic sensors, distance measurement, photo eyes, and then the valve sensors for magnetics. Then the other couple of products that we can offer as well is an IO-Link master. So that takes our IO-Link signals, our IO-Link sensors, and converts them up to Ethernet IP or whatever field bus you're using. And then we've got an IO-Link slave module, which what this guy can do is it allows you to completely get rid of those passive connectivity blocks. This will take digital I/O. If you don't need IO-Link in a sensor, you just want the switching output, you can run that through this block, and then this block can take 12 signals and put it into one port on your IO-Link master. So what we're looking for here is easier wiring and easy interface so that you can see signals from all the sensors on your machine and you don't have to worry about terminating all those pins anymore. And after that, that's everything I got. Basic overview of IO-Link.
Cool, thank you, Jake. Yeah, now it's time for questions. So if you have any questions, please put them in the Q&A section on the right-hand side of your screen. And if time allows, I'll ask Jake these questions. But Jake, we have one question that came in. The question is, I often hear people referencing service or system data and process data. What is the difference between service data and process data?
Yeah, that's a good question. So IO-Link, if we go back to serial-based communication, what we're looking at here is lots and lots of data that the sensor can provide. I mentioned time stamping, I mentioned temperature warnings, we mentioned switching signals. Some of that information is mission critical and the machine needs that as fast as possible. We need that information constantly all the time. And some of that information, maybe timestamps, maybe the device ID, the model number, that's not something that I need all the time. I don't need you to send me that information multiple times per second. I just want you to give me that information when I ask for it. So service data is the information that we get upon request. If I request that information, the sensor will send it to you. Process data is the high-speed data that the sensor is always spitting out. If it's a distance measurement sensor, it's spitting out the distance to an object. If it's a switching sensor, it's giving you the status of that switching output, high, low, as fast as possible. So that's a basic difference between service data and process data.
Awesome. And another question is, what can I do if my process is running faster than the minimum cycle time for IO-Link?
Yeah, that's another great question. So at the top here, when we started what is IO-Link, there were a few parameters that, sorry, I'm not going fast enough, a few parameters here, bullet points about IO-Link. And the fourth one down, the typical cycle time, that's actually the minimum cycle time, is 2.3 milliseconds. So that is actually quite fast for most processes of what our sensors are doing today. But there are a few processes, think printing or bottling, that can get a little bit faster than that 2.3 milliseconds. I need the signal faster than 2.3 milliseconds. When we get into applications like that, typically what we'll do is we'll take this unused pin, so IO-Link only uses pins 1, 3, and 4, power, ground, and communication. We'll use this unused pin 2, and we'll put a high-speed output on that pin. So you don't lose any of the functionality you have in your machine today. We'll run that to whatever cutting head, whatever print head you've got today that's running at high speed, but I also have the ability to get extra information out on pin 4 and all the root cause analysis that I need to be able to do.
Great. Another question is, does it cost extra to get a sensor that has IO-Link versus one that does not have IO-Link?
Another good question. So sensors that have IO-Link versus ones that don't have IO-Link, the beauty is actually a sensor doesn't have to only work with IO-Link if it has it on board. We'll see written on this diagram actually is C/Q. So C is the communication, but if it's not talking IO-Link, it will still give you a standard PMP switching output. So for most of our sensors, especially at SICK, most of our sensors already have IO-Link on board, even in the standard version. So there's rarely a price increase for most of our, especially our new sensors, there's rarely a price increase. There are a few that you can find that are maybe a 5% adder, but no major price increases to go to an IO-Link communicating sensor.
Cool. What are the main differences between IO-Link and ASI?
Oh, yeah, so ASI, ASI, they are different communication networks. They don't communicate together very, very easily. What OSI is a network that is a two-wire based network that can get some extra information out of sensors, but you have to have dedicated nodes, you have to have dedicated sensors to be able to use OSI. OSI is a little bit more, I think it's actually a proprietary-based network that has expanded slightly wider than one company, but it's just not quite as widely used. You don't have as much flexibility in, say, just take a standard inductive sensor that you have in your machine and run it through the OSI network. That can become more difficult because you gotta have dedicated sensors for OSI.
Awesome. Well, that is all we have time for today. Thanks again, Jake. And I do see quite a few more questions come in through the Q&A section, so I'll have Jake follow up with you and answer all your questions. But please visit SICK.com to stay in touch with our upcoming webinars. And thank you, and have a great day.
Thank you.